All right, if you can have your calculators out. So we're going to have our, again, the schedule for this week. We're having our quiz on Thursday. And so I'm swapping these days here. Quiz on Thursday. So today and tomorrow, I just want to focus on antiderivative word problems, rate in, rate out, these problems that we haven't quite seen. I mean, we know the concepts with antiderivatives, with integrals, but this is a big AP topic, so wanted to go over that today and tomorrow. And then Wednesday, we'll spend another day doing quiz review for Thursday's quiz, and Thursday's quiz will just be over area, this method, washer method, and cross-section. Right. And based off what I saw last week, looks like you guys are pretty close to being pretty comfortable with these concepts, so we'll have just another day to do that. And then help sessions Wednesday and Thursday morning. If you need me to help clarify anything, and then Thursday morning I'll go over that last worksheet. I think worksheet 3 in your, or the morning review worksheet in your packet. Okay. Now after this, after we're done with our new content, we're moving into AP review. And AP review, we're still going to have tests and quizzes, but I'm going to kind of organize them in a specific way here. So we're going to have a test over an FRQ topic next week. I'm probably going to make it next Friday, and we're going to prepare for that. Now, once we get into AP review, we're going to have 5 more assessments. Okay, so it'll be 1 test, 2 quiz, and 2 take-home quiz. And the take-home quiz is just if you complete everything, then you'll earn 100 points for those quizzes. But they're pretty long, so I'm going to try to give it to you before spring break, and so kind of chip away at it. And I know also I think senior last day is like May 9th, so I want to make sure that seniors have like a month to, plenty of time to finish those packets. And then for the test and 2 quizzes, we're gonna have 1 FRQ test, 1 FRQ quiz, and then a multiple choice test. But all these assessment grades are going to be buffered by your homework grade. So if you do your homework, I'll be checking homework daily, and I'll also send you a text reminder on exactly when I'm checking. And then as long as you're doing your homework on time, you're going to earn half the points of your quiz or half points of your test. But even if you're late on the test or quiz, even if you're late on the homework, the worst you'll get is 40 out of 50 points. Okay, so if you're late on everything, but you eventually make it up, you'll still get 40 out of 50. But ideally, you do everything on time, so you'll earn that 50 out of 50, and then the test or quiz is also 50 points. Okay, so that's the big picture for us leading into after we get through this quiz, which is trying to get through as much content as we can, FRQ and multiple choice wise in preparation for your AP exam. And I'll let you use calculators on all the assessments. Okay. But on the AP exam, there's definitely calculator and non-calculator section. But I think it ends up coming out to be around like 60% of the test is non-calculator and 40% of the test is calculator. Any questions at this time? right, so let's go to page 1. Okay, just wanted to kind of give some reminders of units of measure. If we take a derivative, we know we are turning that into a rate, right? So if velocity is meters per second, then acceleration will be meters per second because we're introducing another a rate into the problem. But if you take the antiderivative, your units will change in the sense that your rate will now turn into the degree or the unit above it. So if we start off with velocity, which is meters per second or miles per hour, let's say, and if I take the antiderivative of velocity, then I'm up to position, right? Your units will change if you ever push it through a calculus procedure. So if something is at a rate level, the integral will make it, will strip away that time and it'll just get you that unit. So if it's meters per second, integral will take it up to meters. Okay, so just wanted to remind us of that. Okay, so number 1, the rate at which people enter an amusement park on a given day is modeled by function E, defined by E of t. So rate at which people leave the amusement park is modeled by L of t, which is given this, right? Both E of t and L of t are measured in people per hour. So these are both rates, the rate at which people are entering or leaving the park. These functions are valid between 9 and 23. So the park opens at 9, closes at 11 p.m., which is in this case military time, 23 hours. At time t equals 9, there are no people in the park. Well, there are no visitors in the park. How many people have entered the park by 5 p.m.? So if we have a function that gives us the rates, right? And this is E of t is in people per hour. And same with L of t. These are both accumulating these changing rates at which people are entering into the park. So part A, how many people have entered the park by 5 p.m.? So we just want to track or accumulate the rate at which people are coming in. So we only care about E of t because we're just counting the number of people who've entered the park. So what can we do to get this people per hour back up to the number of people? Just take the what? What can we do to accumulate the rate over a period of time? What calculus feature allows us to get from a derivative up to the function? Antiderivative, right? Okay. So we just simply take the integral of E of t from 9 to 17. So we're going to just accumulate this rate. An easier version of this problem would be, imagine the rate was just like, 100 people per hour, right? It's just a nice constant rate. Then I can just take 100 multiplied by the number of hours that's passed, and that would just be a simple multiplication problem. But the fact that E of t is an ever-changing rate, right? Maybe it's 50 people per hour, then it changes to 80 people per hour, then 100, then back down to 90. So it's an ever-changing rate, but still the same idea. We're multiplying that rate over that period of time. Right. So we're going to use our calculator. Go to Y1. You're going to enter So these are messier functions, so it's nice to have them stored under y1 and y2 so that we don't have to keep entering them. We can just call them. So under y1, do alpha y equals to get that numerator and denominator to show up. And then you'll do 15,600 over, and you're using x, right? You always use x, even on paper, they're giving you a different variable to indicate. Okay, go back to your home screen, math 9, integral from 9 to 17, alpha trace y1. So we started with people per hour. After the integral, we're accumulating that rate over this 8-hour period. And so we're able to see that this tells us, according to this model, 6,004 people would have entered the park by 5 p.m. or between 9 and 5 p.m. Okay, part B. The price of admission to the park is $15 until 5 p.m. After 5 p.m., the price of admission to the park is $11 per visitor. How much money is collected from admissions to the park on the given day? Round your answer to the nearest whole number. So we can create two integrals, right? We can figure out the number of people who've entered in the park by 5 p.m., charge them each $15, and then we can find the number of people who've entered the park between 5 p.m. until closing, and then charge each of them $11. So we can take this, right, multiply each of them by what? 15, yeah. So I'm going to write out the full formula, but you can skip this step. You can just say 15 times 6,004. But it's really 15 times the number of people who've entered the park. And then we're charging a little bit less to anyone who comes in after that. So 6,004 people between 9 and 5 p.m. We're charging each of them $15. And then 1,271 people between 5 p.m. and closing. And each of them gets charged $11 for entry. So I rounded this maybe a little too early here, 1271.283. We'll try again. Okay, so what I should have done was taken this exact value, multiply that by 15, because I think it's going to be more of a decimal value here. But it should come out to be $104,048. Okay, part C. Let h of t equal the integral from 9 to t of e of x minus L of x between 9 and 23. The value of h of 17 to the nearest whole number is 3725. Find the value of h prime of 17. Let me break this down step by step here. So this says h of t is equal to the integral from 9 to t of e of x minus L of x dx. Okay. I really can okay, well, let's see. Let's see what they're telling us here. The value of h of 17. Okay, so they say h of 17. That means I'm just replacing every t with 17. So 9 to 17 e of x. And if I split this up, I can split this up into two integrals. Maybe that's just a little bit easier to kind of think about what this means. So this is the number of people who've what? Yeah, enter the park. And this is, what does this mean? Yeah. So if I subtract these numbers and they tell us that number is 3725, what do you think this number represents in the context of what's happening? This is in terms of people, right? What does this mean? Yeah. So you have people who've entered the park, and you subtract out people who've left the park, and this is the number of people who are left in the park at this time, right? So 3,725 people or visitors left in the park or remaining in the park at 5 p.m. We know these units are both in terms of people because these rates have been brought up to the number of people. Okay. All right. So that's what that first part means. And then the second part says, find the value of h prime of 17. So they want us to find the derivative. So let's find the derivative of h of t. So h prime of t would be the derivative of this, right? This is at the integral level. So I want to find the derivative. And if I want to find the derivative of an integral, this should remind us of second theorem, right? We know that if I'm pairing two opposing calculus operations on the same expressions, these will cancel out. What gets plugged in? We just have to worry about plugging in what? All right, remember second theorem, these cancel out, but what gets plugged in? Replace the x with what? Replace the x with, okay, let me review second theorem here. Okay, you guys just did this on the quiz here. What does this turn into? Right, this cancels out f of what? Yeah, f of p of x times p prime, right? So we're just applying that here. So we can replace the x with what? T, yeah. So it's e of t minus L of t times t prime, and the derivative of t is just 1, so it's not going to really make an impact. So h prime, it's just going to be, you know, these two operations cancel out. We're just left with e of t minus L of t. Okay, so now we're at the derivative level, and we can work on what they're asking us to do. So if I want to find h prime of 17, then it's simply e of 17 minus L of 17. Okay. All right, so we can just make our calculator do the work for us here. I have y1 being held by e of t, or y1 holding e of t, and I'm going to have y2 holding my L of t. So I'm going to plug in L of t so I don't have to keep entering them in. So L of t is 9890 divided by t squared minus 38t plus 370. So alpha trace. So y1 of 17 minus y2 of 17. I'm converting it to a decimal here, just so I can have an easier time understanding what that number is. So I got negative 380.281. Now, E of t and L of t are both in terms of what? What's the unit of measure here? Are they people or people per hour? So people per hour. What do you think this negative means? Negative 380 people per hour. Yeah. So this is, you know, that makes sense, right? Typically, towards the end of a day at an amusement park, you would expect the rate at which people are, or rate at which people are leaving the park is greater than the rate at which people are entering the park, right? The park population is shrinking towards the end of the day. People are leaving. So this is telling us that at 5 p.m., the rate at which the population inside the park is changing is decreasing by 380 people per hour at 5 p.m. So yeah, number of people in the park decreasing. Okay. Part D. At what time does the model predict the number of people in the park is at a maximum? Okay. So now, anytime we're looking for a max or a min, it's typically going to be when your h prime is equal to what? When we look for relative max and relative min, that's when the derivative is equal to what? 0, right? So that's what we're looking for. We're looking for where h prime is equal to 0. That's going to be where potentially our maximum number of people is going to exist. So let me just give this this illustration here. E of t, this is the rate at which people are entering the park. What's going to happen to E of t as the day progresses? Is E of t going to increase or decrease as the day, in general, as the day progresses? The rate at which people are coming into the park, is that going to be more at the beginning of the day or more at the end of the day? Beginning, right? So E of t is going to be, it's going to start high, but it's going to eventually come down, right? And L of t is doing what? At the beginning of the day, it's low or high? Pretty low, right? I mean, yeah, there's not many people who are leaving the park at 9:30 a.m., but it's going to be pretty low, and eventually it's going to rise, right? So E of t is falling, L of t is rising in general, and they're going to, maximum is going to occur when they kind of meet, right? Because after they meet, when L of t starts to be higher than E of t, then we can expect this part to be shrinking, right? So we're looking to see when is h prime going to be equal to 0. When these are equal, when they're equal, when they pass each other, that's when the maximum is going to occur. So that's why we're setting h prime equal to 0. Okay, so here's h prime. And if you had to guess, what time would you expect the part to be at a maximum on a normal day? Maybe sometime in the afternoon, right? Maybe mid-afternoon. So that's going to be, maybe our guess as we work through it. So we can set h prime equal to 0, and then we can do E of t minus L of t. So the way that we're going to do this, we could set these equal to each other and actually look for the intersection. But I think the easier way to do this is, why don't we graph this equation and then just look for the what? Look for the x-intercept, right? Graph it, look for the x-intercept. That's an easy way for us to find the solution without having to graph. I mean, we could do this as well. We could graph E of t, we could graph L of t, right? Set them equal to each other, and then look to see where they intersect, the time when they're going to be equal to each other. But I want us to try this method where we can simply, if we do it this way, it may be really hard to find because they could intersect like in the thousands or maybe up on the y-axis. That's really hard to find. Meanwhile, if we just look for the x-intercept, we can just kind of scroll across the x-intercept and see where the graph is going to cross the x-axis. So I have E of t under y1. I have L of t under, L of t under y2. So I'm going to keep these two functions, but I'm going to say y1 minus y2. So if we do alpha trace y1 minus alpha trace y2, but I don't want to see all of these graphs together. That'll be too messy here. So I'm going to go to the equal sign. I'm going to hit enter, and that's going to unhighlight. The function is still there, but it's not going to show up in my graph. So you see how I unhighlighted the equal sign? So I'm just going to graph y1 minus y2. So hit graph. We're not going to be able to see much right now because maybe your window is not quite set up right. So let's see if we can set up our window a little bit better. We know that our x min, x max is basically the time for times for this park, which is between 9 and 23. I'm going to say between 0 and 24, just so I can see around the edges. And if you look at our equations, our equations are in the thousands, right? It's like 15,000. These could potentially be the y-intercepts here. So for y min, y max, I'm just going to pick really large numbers in the hopes that I can see a curve. Otherwise, it'll just be too zoomed in and it'll just look like a straight line. So let me just do like negative 1,000 to 1,000, just because I see my numbers in my functions are pretty large. So for y min, x min, x max, I chose 0 and 24. For y min, y max, I'm just going to choose negative 1,000 and 1,000 just to see what my graph looks like. Okay, hit graph. I'm just looking for an x-intercept here. Okay, so there's my x-intercept. So this should hopefully tell me when h of t and L of t are equal to each other. And this is going to be where the maximum number of people are going to be in the park. And we're expecting sometime in the mid-afternoon, right? So if we do alpha trace 0, because we're looking for the x-intercept, pick a point to the left of the x-intercept, hit enter. Pick a point on the other side of the x-intercept, hit enter. Hit enter a third time. And I got 15.794, which is around 3 p.m., around like 3:30 p.m. Okay. So we're going to experience maximum number of people in the park at 15.794. This is going to be the pattern for a lot of these antiderivative word problems where you find the derivative and you set the derivative equal to 0 and you graph it, you look for the x-intercept, and that's going to be where your answer is. Okay, I want to see if we can do one more here. Let's do page 3. Same process here. We're going to take the integral, and that's going to accumulate our rate over time. So the tide removes sand from Sandy Point Beach at a rate modeled by the function R of t. A pumping station adds sand to the beach at a rate modeled by S of t. Both R of t and S of t are rates. They're both in units, cubic yards per hour. And t is measured in hours between 0 and 6. At time t equals 0, the beach contains 2,500 cubic yards of sand. So part A, typically with FRQs, you're going to see they're always going to kind of try to get your feet wet in the sense that they're just trying to get you into the problem. So it usually starts off a little easier, and then they're going to start building on top of what you found. So part A says, how much sand will the tide remove from the beach during the 6-hour period? So we're talking about removal here. So we're just going to work with which function? Yeah, it's just R of t. But R of t is in terms of cubic yards per hour, but we're looking for how much sand. We're looking for cubic yards. So guess what we need to do? How do we get from cubic yards per hour up to cubic yards? Take the what? Yeah, take the integral, right? Take the antiderivative. We're going to accumulate that rate over the 6-hour period, and the integral will do that for us. So integral from 0 to 6 of R of t dt. Okay, plug that into your calculator. Make sure that you are always in radian mode. And just double check, click on mode, make sure you're in radian mode. You can enter it directly into your Math 9 line, or you can put it under Y1. And again, alpha y equals will get you that fractional feature. So alpha y equals, and then that way you can type in without having to use, it just feels a little bit cleaner. So we do 4 pi x divided by 25. Right, math 9, 0 to 6. Okay, we're accumulating that rate over 6-hour period. And now our cubic yards per hour has now moved up to cubic yards. So this tells us if we follow this model, the rate at which tide is being removed, we're going to get accumulation of 31.815 cubic yards of sand being removed by the tide over the 6-hour period. Okay, part B, write an expression for y of t, which is the total number of cubic yards of sand on the beach at time t. So this is a common formula that that shows up on these types of problems, and I just want to kind of show the basic idea of this, and then we can just apply it depending on which problem we're working on. So here's a formula that's going to show up on a lot of, or that we're going to apply for a lot of these problems. If I'm looking for the total amount of anything, could be the total number of people, could be, in this case, total amount of sand. We're always going to have to keep track of what is the initial amount to begin with. What does the problem tell us is there to begin with at the beginning of the problem? And then we're going to, from that, we're going to add the amount that has been added over a certain period of time. And we're going to subtract out the amount removed. And that will tell us how much there is left over. So if I'm trying to figure out how much is there of whatever I'm looking for, how much is there to begin with, how much has been added, how much has been removed, and then if I combine those numbers together, that will tell me how much is left over. So in this case, I'm looking for the amount of sand. In this case, they want to use y of t to represent the amount of sand on the beach. Okay. Do we have an initial amount at the beginning of the problem? Okay, how much? How much sand is there to begin with? Yeah, so the problem tells us that time t equals 0, the beach contains 2,500 cubic yards of sand. So that's our starting amount. Plus, now the amount added is, we have to involve integral, right? And we have to involve S of t. S of t is in terms of cubic feet per hour, cubic yards per hour. So we want to say from 0 to t, and we'll say S of x. Eventually that x will turn into t when that t gets plugged in, but we're going to basically, S of x is the same thing as S of t. We're just using a slight different variable. We just don't want these to be the same variables. So typically we use x and as a placeholder for that t that eventually comes down. But whatever time that we're looking for, right? Could be 2 hours, could be 3 hours, could be 4 hours. We're just creating a formula that we can adapt to later on in the problem, right? If we want to figure out how much sand there is 2 hours in, we can just plug 2 in and accumulate, use the model to tell us how much sand has accumulated over a 2-hour period, or how much the pumping station has added, how much sand has been added to the beach from the pumping station. Okay, minus, and then the amount removed is the R of t. So let's go from 0 to t, but we'll call this R of x. Same function, we're just changing the variable slightly so that these are not the same variables. Okay, so here's the general model that we can use for this problem, and we can adapt this for any amount of time, right? We can figure out how much sand there is 4 hours in, how much sand there is 6 hours in, how much sand there is 3 hours in. Okay, so now part C, we can just, well, for part B, we don't have to find, it's just asking us to create an equation, so this is as far as we need to go for part B. Part C says, find the rate at which the total amount of sand on the beach is changing at t equals 4. So we want to get down to the rate. We have a function level. So now let's find the derivative of this function. So we're going to find y prime first. Y prime is equal to, right? What's 2,500 going to turn into? What's the derivative there? 0. Okay. And I want to find the derivative of this, which essentially is second theorem. So d over dt. Okay, this looks complicated with all this notation, but really, we're just stripping away the integral and making our way down to s, right? So we know the derivative of the integral. This will wipe out. The x will get plugged in for the s. So I'm basically taking my integral and just stripping it away and just making it come down to the derivative level. So my y prime is just going to be s sub x, right? We know second theorem, these wipe out. I just plug the upper bound into the function. Now my integral has been brought down to the function level. Minus, and then this will just turn into r of x. I just want to show you that full procedure, but you can just go from y to y prime just by looking at your original function. 2,500 goes to 0. The integral will be stripped down to s of x, and then integral of r of x will be brought down to r of x. Right? We're just taking everything and just making it go down one derivative level. Oh, I'm sorry. This should be t here. And this starts off as x. Okay, so my bad. All this should now be in terms of t. So y prime of t is just simply s of t minus r of t. And then find the rate at which the time is the amount is changing. So we just plug in 4 for t. So plug 4 in for s, plug 4 in for r. We should get negative 1.908 cubic yards per hour. Okay, I do want to do part D with you tomorrow, but for homework, I just want you to do page 1, 2, and 3, but leave part D for us to pick up. Okay. So your homework tonight is just to finish off problem number 2. So pages 1 through 3, except for D on page 3, we'll do that together tomorrow. All right, come get your phones. Okay, I'll send out a reminder this afternoon. Homework pages 1 through 3. And also, I've attached the key to the end of your packet. Okay, key is attached to the end of your packet.